The first part of the foundations course concerns shallow foundations. And as much as my colleagues in the Deep Foundations Institute hate for me to say it, shallow foundations are really the default form of foundations. In other words, if you can do what you want to do with a shallow foundation, chances are it's the most economical way of doing it. So the shallow foundations are important. And for reasons we're going to go into, shallow foundations design breaks down into two basic parts. They have bearing capacity, or the strength portion, which we'll talk more about in LRFD, and the settlement or the service portion, which we'll also talk in there. The first part of shallow foundations concerns bearing capacity, and that's what we're going to discuss in this video. There are several topics. First, the types of shallow foundations. They're not as multiplied as deep foundations, a little simpler. There's the whole concept of spread footing design and the procedure to do it. Then we're going to talk about bearing capacity itself, failure mechanisms, the upper and lower bound solutions. We're going to talk about, in terms of the upper bound solution particularly, we're going to talk about the basic solution for continuous foundations, and then how we kind of tweak it for real square, rectangular, round foundations, and other conditions which we'll talk about. And then, and those of course are embodied in the correction factors. We also have talk about local or punching shear, factors of safety, some practical aspects, and last but not least, the issue of the presumptive bearing capacities, which is one that's we've almost left it in the rearview mirror, but not quite. First of all, the types of shallow foundations. A shallow foundation is usually placed within a depth D, and it's the rare shallow foundation that's done it great. Most of them are a depth D into the soil, and which is less than the minimum with B for the foundation. In the case of a continuous foundation, B is all you have, but as you see in this diagram right here, the length L is longer than B by convention, and that's an important convention, and it's one that we'll maintain in our design of shallow foundations. There are, continuous, square, rectangular, ring foundations, circular foundations, and strap footings. There's also wall footings. Wall footings are usually a continuous foundation which bears the load off of a wall continuously. How about that? And then there are mats or rafts, which are very large foundations where the flexibility foundation becomes an issue. Let's start with one important definition. And the definition concerns what is a continuous footing and what is a finite footing. Obviously, there are no real infinite footings. But for purposes of design, if a footing's length is 10 times or more its width, in other words, L over B is greater than 10, then we consider it and design it as a continuous footing. Whereby, if a foundation is less than that, then it's either usually a rectangle down to the point where they're the same, it's a square foundation. That's an important definition. It's one that because it allows us to use continuous footings and infinite footings as a practical design tool, and frequently it's very useful, particularly in footings along retaining walls and slopes and that sort of thing. An example is a abutment or a wing wall footing where the shallow foundation is a part of an axis of retaining wall. In other words, the shallow foundation is part of the retaining wall. We're going to talk about, when we get to lateral earth pressures, we're going to talk about the use of retaining walls to resist lateral pressures, But also with like for this type of thing, which is this is a cantilever wall, the foundation, the wall is also a foundation. In other words, it supports loads this way and also resists sliding loads this way. And we'll get to that when we get to cantilever walls, but this is a situation where the retaining walls and the shallow foundations come together. A combined footing are spread, usually support two or more columns. Sometimes they can be rectangular, sometimes trapezoidal shape. And they can be used to, if the shape and the load, to deal with the issue of eccentricity and concentricity, which we'll talk about in a little bit. Mat foundations are very large foundations that, dimensions from 20 to 80 feet. They are used normally for large buildings, and usually you see them in soft to medium soils. Mat foundations are kind of a very special case. It's where the flexibility of the foundation the interaction of the flexibility of the foundation, the flexibility of the soil is more important with a mat foundation than it is with a spread footing. In other words, a spread footing is in a very localized area. And in fact, if you have it like this, you have a series of columns. Each column can have its own spread footing. But with a mat foundation, you do away with all of that, and the continuous mat is the foundation, and the loads are transmitted from the columns to the mat rather than the columns to the footing and then the soil. So it makes for a different type of design. One thing we're going to come back to, and we discussed some of this in soil mechanics, is the issue of bearing pressure distribution. We talked about the fact that rigid footings and flexible footings have a different distribution. Some of that distribution, and we talked about in soil mechanics about what the effect the theory of elasticity tells us. But here we're going to look at a more practical view. This is a simpler and more practical view of what a rigid footing like with a clay soil. In a clay soil, it's more like elastic theory predicts, where you've got a very high load in the corners of the foundation and a low one at the center. Whereas with a sandy soil where friction dominates, it starts at zero and goes to the high point in the center. So it does not follow the theory of elasticity solution. However, in the case of a very flexible foundation, a uniform load, and then these cases here are uniform loads, which implies either a uniform load or, in the case of a rigid foundation, a concentric load will give the same thing. I want to talk about concentric and eccentricity in a little bit. Whereas with a uniform load, if you have a uniform load, it transmits it perfectly to the soil and you get a uniform reaction. And that's the ideal case. And we talked a lot about that when we talked about Boussinesq solutions in soil mechanics. Many of those, particularly for strip foundations and rectangular foundations or square foundations, are all based on a perfectly flexible foundation. One thing that your FHWA manual discusses, and I'm not going to spend a lot of time on it, is trying to shear failure versus settlement. Do our foundations designed primarily for bearing capacity, or are they primarily designed for settlement? By settlement, which drives them? And the answer is depends. It depends upon the soil. It depends upon the width of the foundation. For example, this diagram shows that the narrower your foundation is, the more bearing capacity dominates. Whereas if you get wider, then the settlement tends to take over. And of course, that depends on a lot of other things. For example, how much settlement can your structure tolerate? That's an important consideration. Bearing capacity is based upon the load, but if you have a certain load on a foundation, then the load that on the one hand, with bearing capacity, the strength of the soil, in a very broad sense, determines what load it can withstand. Whereas with settlement, the more load you apply, the more the thing sinks, and therefore how much it sinks, how much your structure can take, becomes a deciding factor. Now we've turned to the first topic, which is upper and lower bound solutions. And if you recall from soil mechanics, upper and lower bound solutions are basically a way of bracketing plasticity problems in soil. Normally, like an FEA, the two would be actually combined into one. That's one of the advantages of FEA solutions. With upper and lower bound solutions, basically we say that in a lower bound solution, we see somewhere in the system an initiation of plasticity. And in an upper bound solution, we say that plasticity has spread out to the point where we get failure. In other words, particularly we talked about where our model for these two courses is going to be an elastic, perfectly plastic model. Basically what we're saying is we've reached the point with an upper bound solution, we reached the point where along the failure surface, and we talked about failure surfaces and slope stability, we have plastic conditions all the way through, therefore it fails because it can't take any more load. And that's the difference between upper and lower bound. And that's the sort of the crude, practical definition of it. We talked about the more formal definition, which Veroit discusses, and we talked about that in soil mechanics. So the upper and lower bound solutions are a way of bracketing the solution between what we have a high degree of confidence will not fail and what we know will fail. And believe it or not, in bearing capacity and a lot of other parts of soil mechanics, we design between the two. We actually design in such a way that we anticipate that some plastic failure will take place. The question is, how much do we restrict it? In a lot of design, for purely elastic design, we keep everything below the elastic limit, and that's fine. And that's really keeping it below the lower bound solution. But in soil mechanics, we don't normally do that. Sometimes we will. We saw that in cohesion and retaining walls. But in our case, in most cases, we don't. And certainly not in this one. Plasticity, basically the idea is if you start loading a foundation progressively, sooner or later you're going to induce, and basically we do along a failure surface. You've got a nice medium, continuous medium, where a plasticity, in other words, a surface or a line or a surface of plasticity forms. And obviously what we want to do is to prevent that line from completely forming, but if we to prevent that line from forming, we have to make sure we know how it gets there, if it actually did, and then work our way back. So so that's pretty much what we're trying to do in bearing capacity, is to avoid the arriving at the upper bound solution, because the upper bound solution will usually be failure. In principle, this only applies to cohesive soils. We've extended it to we're going to show you an extension of it to using soils with both cohesion and with friction, both cohesionless, cohesive soils, and everything in between. We make a few assumptions. I had a fluid mechanics heat transfer teacher when I was at Texas A&M that talked about if you want to know how an engineering problem goes wrong, the first thing you need to look at is what assumptions you made. and that's a very valuable. Then we're talking about the assumptions. The foundation is very rigid. We're talking about a rigid foundation in this case. We're not talking about a flexible foundation. Actually, we kind of, to be real honest with you, for the lower bound solution, we kind of cheat on that. We actually, for the lower bound solution assume we actually assume a flexible foundation, because the rigid foundation, as you recall, for infinite strips there's no lower bound solution for it, basically, because you get infinite stress in the corners right off the bat. So we assume that there's no sliding curves, which was true. The applied load is compressive and applied vertically to the centroid of the foundation, or it's uniform. In other words, it's a concentric load. There's no applied moments. The depth of the foundation is less than or equal to its width, which is typical for bearing capacity. The foundation is a strip footing. Bearing capacity theory was developed for strip footings, and we, and then we extended it. And we're going to talk about those extensions. The soil beneath the foundation is a homogeneous semi-infinite mass. The Moore Coulomb model of the governing shear failure mode is the general shear mode is the governing mode. No soil consolidation, and the soil above the bottom foundation has no shear strength. There's only a surcharge load against the overturning load. Let's start with the lower bound solution. We have the infinite strip load, which is an extension of Flamont's solution, which we discussed in soil mechanics. And for any point below that, in the semi-infinite space below it, we can compute the stresses in the horizontal direction, the vertical direction, and the shear stresses. And we do so with the equations shown here. Now you'll see these in different forms, but that's what it is, using particularly that angle alpha and the angle beta, which is defined in the graph. However, instead of going through Moore's circle, we note that the principal axis of stress at any point is the axis shown by this dotted line, which is halfway between this ray from the one edge down to a point to the other edge down to a point. Halfway between the two, right here, alpha over 2, is the principal axis. And along the principal axis, the solution is considerably simpler than it is if we don't, if we actually just stick with theta z and theta y and tau. So these are much simpler, and of course there's no shear in the principal axis. Now, one thing you probably noticed right off the bat, or may have noticed, is that there's no it looks like, at least the last diagram is an at grade solution. And you say, well, you told us that there was no, usually didn't design them at grade. Yeah, they don't. So what we're going to do is we're going to do a little engineering fiction here, and we're going to, instead of inserting this into the soil, we're going to define here and here, all around it, some kind of surcharge load. And that surcharge load is equal to the unit weight of the load times its times the depth of it. In other words, the D from the base of the foundation to the ground surface. And so that's how we're going, or gamma, or in this case we call it H. We define the Moore Coulomb failure equation, which you just saw in soil mechanics. And we talked the friction factor is 0, at which point we have failure. And the principal stresses, if we apply those principal stresses to that failure function, we get this at the very bottom of the screen. At this point, I'm going to just kind of walk you through the derivation stress. I have on my website a more complete derivation of this. we determine the depth z, in other words, the depth below the foundation, as at a function of alpha at which the stress is at a maximum. And we can show that alpha, the alpha at which it takes the maximum, is pi over 2 minus phi. In reality, however, the depth must be 0. And we solve, we substitute that alpha into the equations, and we went into this equation, and then we solve for z max, and then we say that, well, z max has got to be equal to 0, so we get rid of that. The grave stresses take place at the surface, and then we solve for the critical pressure by getting rid of the z. We get rid of that, and we solve for the critical pressure, and we get this equation. That is the lower bound solution, at which point, up to that point, all of the stresses in the soil have been elastic, up to that pressure. But when we hit that critical pressure, we start seeing plastic deformation. So that is the lower bound solution. And again, like I said, the problem with that is that there are a lot of problems. Verroy uses a simpler solution based upon, there are a number of ways of getting to that, but he doesn't include any friction, and that doesn't make it very useful. The problem with this is that it assumes the foundation is flexible. So there are issues any way you go with it. But in any event, it's a good way of starting at the bottom. And you'll see what I'm talking about in a minute. On the upper bound side, the solution to this problem actually dates from about 100 years ago, when Prandtl, who is better known for his work in fluid mechanics and specifically in aerodynamics, actually developed this as a solution to the problem of a punch through metal. And he basically developed the upper bound solution that if you did a punch, you developed a failure surface that looked like this. And when this failure surface was completely plastic, you had failure. It went through, you had plastic deformation, irreversible plastic deformation. And basically, he came up with the equation that you see here, where you have 3 terms. The first is a cohesion term. That is due to the cohesion of the soil. The second term is a surcharge term, which is due to the fact that if you have a surcharge here, which you wouldn't necessarily with a metal piece, it will, in other words, if you start trying to rotate this bit of soil out of the earth, this surcharge is going to resist it. So that gives you some extra. The one thing that he didn't do, and Terzaghi added to it, was the effect of the weight of the soil. You will recall, or you may recall from soil mechanics, that the only way a truly cohesive soil will, a cohesional soil has any kind of strength is if there is weight on top of it. If this is the failure surface, and that's Prandtl's, then inside of this there is a mass of soil, and that mass exerts weight on that, and that weight can be along the surface, can be used to resist, much as the case is the case with slope stability. Same thing. And that's the last term, the foundation soil weight term. And these 3 terms are called N sub C, N sub Q, and N sub gamma. And they are defined in this way. This is from your foundations book. It shows you all of the different terms, what they mean. In the case of N sub C and N sub Q, you can actually compute them. I don't necessarily recommend students do that, because unless you're setting up in a spreadsheet, in which case you have to do it that way. The N sub C and the N sub Q terms are pretty well established. And for Terzaghi solution, the Terzaghi was the original one, and it goes back to the 1930s and 40s. Um, when he added the last term and solved the problem. The first two terms, the inst of C, inst of Q, pretty much everybody agrees on those. Inst of gamma is one of those things that geotech hasn't quite settled down on. So you have, it depends on who whose theory you adopt. You've got DIN Bridge Hansen, CFEM, or Vesage. In the United States, AASHTO has decided on Vesage gamma for inst of gamma, which is right down here at the bottom. But the easier way to do it is to use this table, which is in your book, and which those are the Vesage upon which the Vesage AASHTO factors are based on. They are strictly functions of the phi of the friction angle. That's all they are not functions of anything else. So if you see some formulations that don't have them, those are not true. They're strictly functions of phi. Let's take an example. We have a foundation which is 5 feet deep and 6 feet wide, which means the B is barely wide enough to make it as a shallow foundation. Gamma, both above and below the foundation, 125 PCF. C is equal to 500, and phi is equal to 20. You can see that right there, by the way. And so how do you get it? Well, I'm going to leave it to you to do the math, but I will show you where it comes from. If you know phi is 20, C is 500, what that means, first of all, the lower bound solution is pretty much, let's go back, is pretty much direct substitution. Since lower bound solution assumes that gamma is the same above and D, phi, make sure that your phis are in radians when you can make these computations. Because sometimes they appear outside of the trigonometric functions, gamma, and all you do is just plug and chug. And I suggest you take the numbers you have there and plug them and chug them. Upper bound solution is you simply plug them into this equation. You have to compute, before you compute that, you have to determine your inst of Q, inst of C, inst of gamma, and you do that from the tables. 20 degrees, the table is right 20, right down here. You can just copy those over if you like. And then you simply substitute the C. The only thing that you have to do that you don't do with lower bound solution is you have to compute the Q, the surcharge. And the surcharge is simply determined by taking this unit weight right here and multiplying it by this depth. So you take 5 times 125 is 625 PCF. And that's it. That's all there is to doing a strand. This is for a continuous footing in both cases. The lower bound solution only applies to a continuous footing, and the way that I've put it, the upper bound solution is likewise. We're about ready to get into situations where that's not the case. Now we have talk about types of bearing capacity. General shear is what the theory is based on. Local and punching shear are generally found in softer soils. And once you start getting into lower and punching shears, you get into issues with bearing capacity, but also with lower strength soils, you're going to get more settlement. So that's becomes more of an issue with those soils than, say, it is higher strength soils where bearing capacity becomes more important. However, we do have a correction, as you see here. You basically, instead of AASHTO recommends a correction of C and phi for these different conditions, and you need to be aware that is actually exists. So that is a correction for those. But again, I say with softer soils, you really need to start watching for settlement issues, and settlement issues can be very deadly. We'll talk about those later. Correction factors. Correction factors are not introduced to first of all, once we get past the conditions that we use to develop the theory to start with, then the lower bound solution pretty much is in the rearview mirror. We're strictly dealing with upper bound plus some kind of factor of safety. Bearing capacity solutions, however, we use the correction factors to extend bearing capacity, and this can get tricky sometimes. We have shape correction factors. We have S, B are the base inclination correction factors. C, the capital C factors are groundwater factors. D is an embedment depth correction factors. I'll get to that. I'm not real fond of that. And then, of course, the N sub C are the bearing capacity. They don't change. We're going to stick with them from the original theory, and then we actually use the other factors to correct or to apply those bearing capacity factors to the situation at hand. The most important ones are the shape. And oh, by the way, I'm sorry. If you look at Q ultimate over here, you'll notice that instead of just the C, N sub C, you've got S shape factors and base inclination factors, and then you've also got groundwater factors and embedment depth factors multiplied to that. That is the complete bearing capacity equation, and that's what you could actually use that in all your calculations. Is just that for infinite strips we talked about, all the factors go to unity for the original conditions. The shape factors are the most important because the most important correction is actually for the shape of the foundation. And and whether the shape factors depend upon the friction angle. And all you do is you take that chart and you apply those B and L. If L is, if B over L is 0.1 or L over B is 10, then you ignore those and make them unity and you go on. But for square and rectangular foundations, this is what you use for shape factors. Inclined base factors are in case they slope it this way. The problem with inclined bases, they have been used, is they're a little tricky to build, particularly in cohesionless soils. I'm not going to spend a lot of time there. I'm just going to warn you the existence of inclined base factors. There are other ways. They've been used to have, if you've got a flat foundation, if you've got lateral load on it, and lateral loads and shallow foundations don't like each other very well. The only thing you can do, the only thing you have is the friction between the two. Well, other than the foundation and the soil. Well, there are other ways of achieving this. We'll talk about keys and that sort of thing. And of course, occasionally, if it's bad enough, then you'll have to do some kind of piled or deep foundation to help your shallow foundation. The groundwater correction factors take into consideration the fact that for cohesionless soils or soils with friction, the strength of the soil is determined by the unit weight, which is pressing on whatever failure surface is resisting failure. If your effective stresses drop, which they do when you get groundwater, then the effect of then the ability of those soils to resist friction decreases likewise. And the groundwater factors take that into consideration. There are two of them. The CW gamma takes into consideration the effect of groundwater for the for the soil which is trapped under the foundation, between the foundation and the failure surface and the surface. And that for soils where the groundwater table is above the base of the foundation, which happens occasionally, it's not really the best thing to do, but it does happen, then basically we assume that the strength of the soil is cut in half. If the table is between the base of the foundation, somewhere maybe a time and a half times under the base where you figure the failure surface stops, then it depends upon how far up or down. You do a linear interpolation as given in the instructions. The CWQ only applies if the only affects it if the soil, if the groundwater table is above the base of the foundation. It basically reduces the overburden that you have because it reduces the effective stress the overburden causes. And this is probably the simplest way. There are other ways to do this, and of course you get into layer soils, that's a whole different ballgame. The last one is embedment depth factors. The short answer is don't. Embedment depth factors assume that the failure surface extends all the way to the surface of the soil instead of just the base of the foundation. Because fill is an unreliable thing in terms of its consistency, particularly if they're just covering up whatever it is, don't do this. And I see this every time I give this. Students will dig into the embedment depth factors and try to use them. There's no sense in having them. No, do not include them in the calculations. Load inclination factors, I do go through a lot of verbiage. There's a lot of different ways of handling this problem, one of which would be to reduce the load on the foundation to its component and treat the vertical component just like you would any other load, and the horizontal component like a frictional load. There are a number of ways of doing this. I don't spend a lot of time emphasizing the issue of load inclination factors. You do get into that to some degree when we get to retaining walls, but we just split up into components. Now we get to allowable. This is where the lower and upper bound scheme starts making more sense. We cannot design a foundation. There are two things you have with bearing capacity equations. The first is the fact that if you design a bearing capacity with a factor safety of unity, you will have failure. The theory tells you that. The second thing, of course, is that like anything else in foundations, there's always uncertainties to the properties of the soil. Between the two of them, you don't really want to design a shallow foundation with a factor of safety of unity. You want to have some kind of factor of safety. And typical minimum factor of safety range from 2.5 to 3.5. Obviously, probably the highest factor of safety, if you could get it, would be a lower bound type solution. And in fact, there are situations where a lower bound type solution would be appropriate. They're not very often. The problem is that lower bound solutions have not been developed very well for shallow foundations. Other than the one that I showed you, they're not common. So, and they have their limitations. So normally, that type of factor of safety is reasonable. And so we have, and so that's why we have factors of safety in this particular field. And let's take an example. Square shell foundation 5 by 5, foundation depth of 2 feet. The soil is cohesionless. If I say it's cohesionless, then C is equal to 0. The unit weight is 121 PCF. The internal friction angle is 31 degrees. The load in the foundation is 76 kips. Groundwater table is very deep. Factor of safety against bearing capacity failure. Now, I want to emphasize something that I do and trip students up frequently. When there are two ways of looking at a factor of safety. I could set this problem up. Okay, you're going to design it, you're going to determine the ultimate, which is your upper bound solution. And then you're going to reduce that by a factor of safety to an allowable. Or I can say, all right, I've given you a load that I actually anticipate. I want to know the factor of safety based upon the ultimate. And then you would divide the ultimate by the allowable, you get a factor of safety. In other words, the load that I tell you I apply is a de facto allowable load. So you can get the problem either way. The governing equation, as always. We can neglect factors due to the groundwater table because this other groundwater table is very deep. Load inclination and depth, I've talked about why I don't think we need to be worried about those in this course at least. First, bearing capacity factors for 31 degree inclination is we just take these straight off the table. The shape factors are fairly straightforward. Actually, the S of C and the S of gamma are the same. Those are shape factors for square foundations for any square foundation. S of Q depends upon the friction angle. And you can see what that amounts to. The calculation is fairly straightforward. Again, C is 0. The Q, the overburden, is the unit weight of the soil above the base. It can be different. It can be different above and below. And in this case, it's not. And gamma is equal to 121. That's one thing you need to watch. That's one reason why in the bearing capacity equations we define Q the way we do. Because, for example, you get a bunch of, you excavate down to the depth, and then you pour the foundation, and then you get a bunch of, they throw the soil on top of it, and they may not be as careful. They may not be as careful. So the soil on top of it, for example, could be 115 or 110 PCF, in which case your overburden is less. So you have to take that into consideration. It's a straight up substitution. Just plug and chug as you see right here. And you substitute and you get 12,695 PSF. Then you compute the ultimate load, which is the QL times the area, which is 25 square feet. 5 times 5 is 25. And you get 317.3 kips. You divide the ultimate load by the load you're applying, which is 17, you get 4.17. You can also do it using pressures. For uniform pressures, you can actually do it either way. Either way works. Groundwater. Groundwater gets into the issue of what's really below the surface. We up to now we've assumed a homogeneous mass of soil which has the same soil properties all around. Groundwater is one thing that could mess this up, and another thing is layered soils. There are three ways of, you got several layers. There are three ways of doing it, and I've taught differently over the years which is which. You can use the lowest values of shear strength, friction angle, and unit weight below the foundation. If you've got several layers, in the region. Usually it's either B or 1.5 B, and 1.5 B is probably the best. It's the simplest but the most confusing. And then use the groundwater tables in conjunction with that. That's the simplest and most conservative. Use a weighted average. Weighted average is what I taught for a long time. The only thing that trips up weighted average, other than being complicated, is the fact that if you've got a very, very soft layer, the very soft layer will drive the whole thing, and you'll have problems. If you've got a very soft layer, and of course you could go through the trial services. I wouldn't recommend that. If you've got something that complicated, you probably need to do finite element analysis. And the groundwater, we're going to use the correction factor. It's the simplest. So, for example, we have the previous example, and the groundwater is 3 feet below the base of the foundation. Note that the groundwater factor is based upon dW, which is the distance from the surface of the soil to the groundwater table. That for CW gamma. This is a tricky thing, and we're going to see this again when we get to settlement. There are two data actually, to be correct. There are two data that we have in this. One of them is one of the data is the surface of the soil. The other one is the base of the foundation. The groundwater factors are actually based upon the surface, and you need to be aware of that. So the depth of the water is 5 feet, and so therefore for the CW gamma, they're basically the interpolation. At the base of the foundation, the two are 1.0 and 0.5, and then at the base of the influence zone at 1.5, it's 1.0 and 1.0. If we interpolate, the CWQ is the same. If it's 1 in one place and 1 in the other, it's going to be 1 in total. And then CW gamma 0.5 to 1, you interpolate that, you get 0.7. That's how you use the groundwater factors. You compute them for groundwater tables that's below the base of the foundation. You compute them for the at the base at 1.5 times below B, and you interpolate. If you had a groundwater table above the surface, you would basically, any effect below it, is going to be half. Every your the CW gamma is going to be 0.5, whereas no matter what, but you can do it the same way. And the CWQ is going to be interpolated. So, and you would take the interpolation from the surface down depending on where that was. So you have to be careful to look first where the groundwater table actually is before you start interpolating. But anyway, doing all that, substitute and solve like we did before, we get 11,200 APSF, which represents an 11% decrease in the bearing capacity, which for the load applied is not a big deal, but if the load were closer to that, it would be a big deal. We've talked about all of our workarounds, or maybe extensions is a more appropriate term of bearing capacity theory. And now we're going to talk about load eccentricity and footings on top of slopes or on slopes. Eccentric loading of foundations. Foundations are ideally located concentrically, but that's not always the case. If you're up, for example, on a very tight situation with a footing and a property line, and you need to put the wall as close to the property line as you can get it, sometimes it's impossible for the footing to go over the property line, so it has to come back, so you get an eccentric load. Eccentric loads, eccentricity, that's defined as eccentricity, is the distance from the effective point of loading to the centroid of the foundation. And the distance can be one way or two ways. In other words, with a strip footing, you only got one way to go. With a square or rectangle, you can go either the X direction or the Y direction. or both. And it's important which one is both. A moment, you can have a moment, but the easiest way to deal with a moment is to essentially use the moment arm as the eccentricity and move whatever load you've applied over there. That's usually the easier way to do it. Ways of accounting for eccentricity. There are two. And this is another great source of confusion amongst students. There are, one of them would be to is the fact that if we assume a uniform load, if we start shifting a load over, it produces, instead of a uniform load, a ramp load. And that is one method. That method is used in some bearing capacity. Sets the maximum. The maximum pressure you actually experience anywhere is it. The other one, and that's normally, you see that particularly with for structural purposes. You could use that because with structural analysis, you could is more appropriate to use that. For geotech analysis, most of the time, and this is a point where students a lot of times just miss the boat, is the issue of the reduced foundation side. I'm going to talk about that, but the reduced foundation size basically assumes that instead of a full-size foundation, the eccentricity reduces the effective size of the foundation. And in other words, you have a load, which becomes, instead of essentially a way of transferring an eccentric load into a concentric load by reducing the size of the foundation. The base of the new, for example, B is equal to the full B minus 2 times the eccentricity in the B direction, and L sub F, the reduced length, is equal to L minus 2 times eccentricity in the L direction, E sub L. So you get a reduced foundation. Once you get a reduced foundation, you can use that to analyze your geotechnical failure or to design against it. These are some terms that we use for low eccentricity and inclination. This is a diagram that shows the eccentricity of footing, and I would suggest that you study this carefully, because if you don't, you're likely to end up with problems. Very likely to end up with problems because it's a difficult concept for some reason, but basically what you're looking at here is the following. We have a full-size foundation, and we basically, if a load is eccentric in this direction, let's say just one direction, then basically we do is we reduce it to this using this formula, and if it's in two directions, we use both of them. And we'll end up with a new B sub F reduced and new L sub F. And we use that. And obviously the effective pressure goes up. For geotechnical purposes, this is the standard way of doing it. And it's not, I would suggest you study it carefully, because it's not a particularly, it's not a difficult concept to grasp, but for some reason, students have a hard time grasping it. I'm not really sure why. Irrespective of which way you do it, there are two types of eccentricities. One is one-way loading. One-way loading is loading along the center axis of the foundation. it's for continuous foundations. Obviously, there's only one-way loading because you can't move the load. The infinite doesn't allow that. In the case of a finite foundation, one-way loading can basically be true if the load is eccentric only in one direction. But basically what happens is that as you move the load in one direction, this happens. You start getting a ramp load. You get here and here. And then you get to the point somewhere out there where this load goes to 0 and this is your maximum load. And then if you go past that, you can't get negative load, so all the load is positive and it goes this way. This is not really. There are certain fields where this load would be acceptable. You see this sometimes with retaining walls, levees and retaining walls. Not in this course. In this course, we assume that if the eccentricity is that far over to the point where you start getting liftoff on the side, then you don't have any business doing it. Let's take an example. We have a continuous foundation is shown, one-way eccentricity for sure. Groundwater tables at great depth, we won't try them. And the way the foundation is not included in the load shown. Whether the result acts in the middle third, I'm going to explain what that is in just a minute. And minimum and maximum bearing pressures and reduced bearing area. Compute the weight of the foundation. W over B, which is weight per unit length, is equal to 1,125 pounds per foot. It's 5 feet wide, 1.5 foot deep, times 150 PCF. Now, compute the eccentricity. Eccentricity is equal to that moment divided by this load. And you do that, you get 0.61 feet. Now, what's this middle third thing? Let's go back a couple of steps, and we looked at this. If you reach the point where you have a zero load here and a maximum load here, that takes place. The eccentricity is equal to 1/6 of the B of the foundation, or L, if you got two-way. 1/6. That can be shown that it's 1/6. The resultant. And by the way, I have a whole little thing on resultants too, so I would strongly suggest you look at that if that concept throws you. I have resultants. If that resultant is at a point which is only from the center axis of the central of the foundation to there, is less than or equal to B over 6 eccentricity, you are in the middle third. Why, you ask, is the middle third? Because 1/6 plus 1/6 is 1/3. So if you have that, you will have the middle third. And once you, as long as the foundation's in the middle third, it's acceptable. If it's not, you'll get this condition. And this condition is a no-no, at least in this course. I say there's a few places you can get away with that, but not most of the time, no. So so in any event, that's the middle third. So we go over to compute the eccentricity is 0.61 feet. The moment. Now notice carefully that on the Q, the 12,000 is the load and the 1,125 is the weight. The weight of a foundation is generally a concentric load. In other words, if a foundation is a uniform thickness, the load is going to be, the resultant of the load of the weight is going to be concentric, which will pull the eccentricity back. So B over 6 is equal to So B over 6, the middle third dimension is 5/6, is 0.833, which is greater than 0.61. And the eccentricity is in the middle third. Now, for one-way pressures, we can use these equations. The Qmax and the Qmin. You recall, let me just go back up there. You get this kind of thing. And the Qmax, Qmin. And the Qmax is equal to, with a foundation weight for either continuous footing, which is at the bottom here, or for finite square with only one way of eccentricity, it's up here. Now, let me give you a little hint. If you don't like the middle third concept, you can the way you get around this problem is you can compute both the Qmax and the Qmin. As long as they are 0 or positive, both of them are 0 or positive, or greater than 0, or equal to 0, you're in business, because both of them, you don't have liftoff. If you have a negative, you're out of the middle third. So you can compute them either way, and you can compute them both ways if you want to. If you're going along, chugging along, and you compute, say, something that looks in the middle third, and then you compute the Qmax and Qmin, and all of a sudden one of them is negative, then you know you've got a problem somewhere. So, for this problem, this shows you simple plug and chug. You plug those in those formulas, and it shows you how to do it, and you get 45, 46 is the maximum, 73 is the minimum. They're both positive. It's in the middle third. And of course, let's see what our reduced foundation is. Our reduced foundation is the B prime is equal to B minus 2 times the eccentricity in the B direction. And I just plug that in, chug it, solve it, is 3.78. What I would do in this particular case is I would design this foundation as if it were a 3.78 foot wide foundation as opposed to a 5 foot foundation. That's the way I would do it. That's for geotechnical purposes. In other words, for bearing capacity, settlement, all that good stuff. Now there's some ifs, ands, or buts, and I've got them buried. They're buried in your book, and they're buried elsewhere. But there are ifs, ands, and buts to that, because that's another one of those things that we haven't quite worked out yet. But that's pretty much what you. Yeah, that's pretty much the way we do it. Two-way eccentricity means the eccentricity in both B and L directions. It produces a planar distribution of stress. Now, this is another place where students trip themselves up. The kern of stability, this is the little diamond shape you see right here. When you've got two-way eccentricity, it's very tempting to compute one way and the B way and the L way, and if they both match, to declare victory. Don't do that. Basically what you need to do is to compute using this formula right here. If you know your E sub B, you know your E sub L, you simply compute that formula. If it's less than unity, you're in business. Because what happens is that even though it can be less than this and less than this, it can be still out here in this region here, here, and then you're out of the current, which means it doesn't make it, you've got liftoff somewhere. And actually the liftoff problem it can all is the same deal I told you with one way works with two way. If you compute, use this equation right here, and you compute all four of these, and you got four combinations, because you notice there's two plus or minus, one plus or minus 6 EUB, and one plus or minus. If you do all four combinations, you compute all four Qs, then if any of them are negative, you're out of the current. So it's a check. Use it. This is especially important in this one because it's easy to declare victory too soon if you have not taken the current properly into account. As an example, we have a grain silo design. There's four of them. Each silo has an empty weight of 29 meganewtons. The can hold up to 110 meganewtons of grain. The weight of the mat is 60 meganewtons. The silos can be loaded independently of each other. In other words, you can load one in any combination. Whether or not the eccentricity will be met with the various loading combinations possible, and eccentricity can be one or two ways. So, let's start with loading two on one side. The largest adjacent, the Q, is equal to the total weight, which is 4 times 29, where there's 4 silos at 29. You've got 2 times 110. 2 are full, so 2 times 110, plus 60, which is the weight of the mat. You get a total weight of 396 meganewtons. The moment is simply equal to the moment arm is here. It's 12 meters. It's not the greatest shown, but there it is. 12 meters from here to here, from the center line, central here, out to here is 12 meters. It's 12 meters times, there's 2 of them, and they're each weigh 110 full. So you get 2,604 meganewtons per meter. The eccentricity for one way, for 2 full and 2 on the opposite empty, is equal to 2640 over 396, or eccentricity of 6.67. Now, the one-way eccentricity actually doesn't matter whether it's this way or this way. In other words, either these two can be full, these two can be full. It doesn't matter. It makes no difference. It's square. B over 6 is equal to 50 over 6, which is equal to 8.33, which is bigger than 6.67. Therefore, we're in the current on that one because we only have one-way eccentricity. It's symmetric. Now, you could, if you wanted to, say, well, I don't like, this is a two-dimensional problem. That's fine. You can do that, just put E sub L equal to 0. You will get the same result. Two-way eccentricity, we're only going to load one of them. And E sub B, and it's actually gives the same eccentricity in the B direction and the L direction, which is equal to the M, which is 1,320. And again, you can see how they over 286, which is the weight with one silo loaded, is 4.62. Now I'm going to use this formula. I'm not going to compare L and B, and where I'm going to use that formula, and I come out, that formula being, let me back up, this puppy right here. I'm going to use that formula. And I'm going to and put those two E sub B and E sub L in there. And I'm going to, I come up with 1.11, which is great, which means it's not in the current. That's an amazing result. You know, we've got 2 silos loaded. You think, well, that's going to be the worst case, or at least worse than this. It's not. It's actually, the worst case is you only load 1 silo. Okay? Now, there's a couple of ways of dealing with that problem, one of which would be to increase the size of the mat. If you increase the size of the mat, actually what you would have to do to be real picky about this is increase the weight of the mat. The weight of the mat, however, tends to be conservative. So for a first, for a first cut, this would do it. But increasing the size of the mat by 5.4 meters actually solves the problem. And actually more than solves the problem, because if you increase the weight of the mat, it'll tend to shift, it'll reduce the eccentricities. So we do the expanded foundation. If we just stick with that one, then B and L is equal to 55.4, and then we just use the equivalent footing dimensions using the same formulas we had before, and actually B and L is the same, and reduces to 45.8. So in other words, instead of having a 50-foot section or a 55-foot, we would have a 45-foot. Now, if we go back to one-way eccentricity and we want to compute the expanded foundation, and we can see the expanded foundation would do that, we do it that way, and we get, however, this is important. I went to the expanded foundation on both of them, which makes sense. And then what you would do is you would then put, B prime and L prime are different. Notice here that there's no, in a two-way, there's no eccentricity in the L direction, but only in the B direction. So instead of having a square foundation for analysis, I would have a rectangular foundation where my B is 42.1 and my L is 55.4. Couple of notes. This is the fine print on my statement about Meyerhoff's method of reducing the foundation, which is what we've been talking about, the reduced foundation. Again, I think as a general rule, you can design using those, but there are some fine print you should be aware of it. Bowles recommend that the shape and load inclination factors should not be combined, and also in certain configurations, using inclinations with shape factors that are adjusted for eccentricity. Like I said, there's more than one way of handling the issue of eccentric loads. So these is the fine print you should be aware of those. The last major topic I'm going to take up, well, actually we got presumptive to go, but in terms of computational, is bearing capacity of foundations at top of slope. This was originally proposed by Jeffrey Meyerhoff in the late 1950s. And unfortunately, I've never been able to find a really easier way of dealing with this. Like a lot of stuff in the 1950s, the researchers would present these charts knowing that most of the engineers using it would never have any, didn't have the computational power to deal with it. Well, that's changed, obviously. You can do a lot of this stuff in a spreadsheet. And so I'm going to try to go through this as easily as possible with an example. The Q ultimate is equal to this equation right here. And it only has two factors. There's no surcharge term in there, so we're not going to worry about surcharge. There are two different cases. One where is at the top of the slope, and one where it's on the slope. These should be avoided if possible, particularly the ones on a slope. Slopes have enough problems without having to get into foundation loads on them. So basically the trick behind this, and I want to concentrate mostly on this case, is there are two different, these charts are based upon this axis is the distance of the foundations from the base of the slope, and which it is depends upon how you compute your stability factor and some not. So you need first thing you need to do in any of these problems is compute your stability, or determine your stability factor. That's the first thing you need to do. Then from there you can decide what B means, and then little b, and then from there you can decide. Then you've got the next thing, which is D over B. These charts are to assume two different conditions, and you have to interpolate between them. One of them is D over B is equal to 0. You've got a ground surface foundation, very unlikely. D over B is equal to 1, which is the maximum for which is the widest you can have, or the deepest you can do for, and still call it a shallow foundation. Let's do an example. I'm going to go back and forth. Strip flowing on top of the slope. The soil is, is a purely cohesive soil. C. If I tell you C is 17.75 and gamma 10, if I leave phi out, it's 0. On the other hand, if I give you gamma and phi and leave C out, C is 0. So keep that in mind. H is 8 meters. The height is 8 meters. The B, the width of the foundation, is 3 meters. And the D is 1.5. That's the depth. And little b is equal to 2, which is from the top of the slope back to the foundation. In other words, this dimension right here. All given in those charts. Ultimate using solution. First, B is 3 meters, which is less than height of 8 meters, so n sub naught is equal to 0. And that is given in figure 8-18D. What that is, this right here, like I said, this is the first thing you do, is this. And you move from here either to here or here over to here, depending on what soil you've got. Okay? Obtain n sub c cubed from figure 818E for case 1 with n naught is equal to 0. That's the first thing you do. And you have to compute two ratios. D over B is equal to 0.5. And little b over big B is 2 over 3 is 0.667. 2/3. The solution, now, once you've established those variables, then you can start solving the problem. Solution is n sub CQ is if D over B is equal to 0, the slope angle of 30 degrees, and the slope angle, by the way, you'll notice that these have different slope angles associated with them, and you need to read what they are. The broken lines are for D of B is equal to 1, and the solid lines D of B is equal to 0. And you'll notice that the stability factor, this is n naught is equal to 0, and that's n naught is equal to 0. So you got all those. And NCQ for D is equal to 1, and the slope of 30 is 6.4. In other words, we're reading off of D over B. Oops. Go back. D over B is 0.5. We're reading up this way. D over B is equal to 0.5. Or no, B over B, excuse me. B over B is equal to 0.5. And then we get those 4.9 and 6.4. From there, you can then linearly interpolate between the two based upon D over B and get 5.7, which in this case is the average because it's halfway between one and the other, between 0 and 1. And gamma Q is equal to 1 since the soil is purely cohesive. B over 2 is equal to D. Therefore, the shapes factors are unity because it's a continuous footing, and we're not going to consider water table and bedding factors. So once you've gotten that, you plug and chug and get that. And that's how you do those for cohesive soil. It's a little tricky, and it takes a little bit of thought to get through that. I wish we could, basically have a formula. And irrespective, one thing about it is irrespective of how complicated they are, formulas. I've found situations where you would even exceed most practicing engineers' ability to put it together in some problems. But this isn't one of them, I don't think. Required footing setbacks. There are codes that exists that force a footing setback. That's a good idea. Slope stability is a complicated topic, as you saw it originally, because just to get the slopes built without it requires a iterative process. Today, a lot of stuff is done using software, and it's you could include all kinds of stuff. You could include the existence of soil nail walls on the slope. I've got software on my website which actually does that. About footings on slopes, you could do that. All kinds of stuff that can be included. So, but it's good to have in your back pocket method of checking what you're doing, because it's easy to make a dumb mistake, either inputting a dumb mistake or not understand what your software really needs. And once you've made a dumb mistake like that, you're stuck with it, unless you've got a way of checking it. Practical aspects of bearing of foundations. There's some I want to mention. One of them, review your test data. That's this one. It is important before, even with a shallow foundation. You don't have to go as deep as you do with a deep foundation, but it's important to know your soil data. It's important to review a site soil data. It's important for a site to have a proper soil plan, a proper exploration plan, and to have the data necessary. It's possible that if sites have severe non-uniformities, and around here severe non-uniformities are more almost the rule rather than the exception, then you may have then you need to deal with the fact that certain parts of the site will drive the design. So don't just say, well, this all got all this soil, we'll just run with it. In some stratigraphies you can get away with that, but some you really should not do that. The second thing is about the substantial downward movement of the footings required. Basically, what you need to do in that particular case, that's also tied up with a settlement issue. It is true that to mobilize the full bearing capacity of the soil, you do require downward movement, but and to some extent, the theory behind bearing capacity has not taken that into proper consideration, because it normally has assumed, and I don't think I put this out, plastic, purely, essentially a purely plastic model of soil. In other words, it doesn't move until it's plastic, then it starts moving. Soils move from the time you start loading them, and the elastic purely plastic model is better at predicting that. You need to combine any soil analysis of bearing capacity with analysis of settlement. Not only just to fully mobilize the soil. I want to talk about mobilizing soil resistance a little more in deep foundations, but you need to keep that in mind. And last but not least, this is a topic that you see varies: net versus ultimate bearing pressure. In certain methods, like Schmertmann's methods, you use the net bearing pressure, and we'll talk about that next time. But with shallow foundations, main foundations, we talk about the net bearing pressure on the foundation. And basically, the net bearing pressure is the gross bearing pressure minus the overburden, or the Q factor in the equations. For most foundations, I think you'd be better off if you're not worried about that. That alters the bearing capacity equation a little bit. The approach we're taking here uses the gross, which would include loads and the weight of the foundation. We also talk about failure zones for bearing capacity. I would read that. Basically, the way that works is that directly under a foundation, you have a triangular mass of soil. In other words, from the edges down this way, this zone 1. And then that zone 1, once it gets trapped, it starts pushing in one direction or another. In other words, we talk about going one direction. It usually goes in one or the other, depending on minor eccentricities in the load, which way it actually goes, or in terms of possibly even non-uniformities in the soil can affect that. So that's a kind of an overview of the failure zones in soils, and I've kind of glossed over that, but it's something you need to look at in detail to understand how this actually works. Now it comes to the very last topic, which is presumptive bearing capacity. I said I thought the last one was the last one, but this is really the final. Traditionally, shallow foundations were designed using a presumptive bearing capacity, or at least the codes were set up that way. Basically, what they would do is they would say, well, for this soil, need to go beyond, 500 psf or 1,000 psf or whatever, and this is the way you should design your foundation. And many codes, New York's is a good example of that, are based on that. In other words, they give you a limit as to what or traditionally have given you a limit as to what your bearing capacity is. You take that. If it's an eccentric load, you simply reduce it using Meyerhoff's method, and then you live happily. You just apply it, and that's it. We've gotten past that for the most part. You will see presumptive bearing capacities in codes, and if it's in a code, you need to deal with it. Sometimes it's very difficult to get an exception for a code, even when it makes engineering sense. But there's one place where we do use them more often, and that is with rock. Rock doesn't fail the same way. It fails a little differently than soils. The biggest difference with rock is going to be the biggest difference is the fact that rock has fissures in it, and fissures will draw. Soil pretty much covers up the fissures because it's fissured into particles to start with. Whereas rock, you have solid rock, and then you've got rocks with fissures, and of course in this area, rock's very much fissured business. So basically, it's fairly simple. You take a foundation, you determine the load. If you have to reduce it using Meyerhoff's reduced foundation, you reduce it. Once you reduce it, then you compute the actual, you take the load and then you divide by the area, you get a pressure. You compare that to whatever rock pressures you can endure, and then voila, you either have it or you don't. These are useful values. Probably, in one sense, the most useful values are the ones down there in the lower, these, where our Ralph Peck's using RQD. And RQD is something, as I said, we did when back in the original in soil mechanics is one of your first lab experiments. RQD is a very useful, and again, RQD emphasizes the fact that the big variant in rock is its integrity. If it's solid rock, you'll get one result. If it's not solid rock, you'll get another result. And that's interesting that you can actually allowable pressure based strictly upon the RQD, which is a fairly common test that you run when you've got rock in a soil rock profile. So that's probably the one that I will emphasize more than any other here. If there's other data available, obviously you'll want to use it, but for general use, this is pretty useful. So that's the first part of for our discussion of shell capacities. Until next time, thanks for watching, and God bless.